All right, buckle up because we're diving into the deep end today with Tsallis Holographic Dark Energy. Whoa, even saying it is a mouthful. You sent this research paper in, and let me tell you, it's a dense one. Clearly, you're trying to wrap your head around this whole dark energy mystery, and not just the basics. We're talking about how this specific Tsallis model shakes things up. We'll unpack how it tackles the evolution of those massive structures in the universe, galaxies, clusters, you name it all, through the lens of this new dark energy model. Get ready for some serious aha moments, those insights that make you see the cosmos in a whole new light.
And the beauty of this paper, it's not so much about groundbreaking new ideas, but using a fresh lens to examine a familiar problem. Think of it like swapping a magnifying glass for a high-powered telescope.
I like that. Okay, so back up for a second. For anyone just joining us, what exactly is dark energy?
Yeah.
It's like this phantom force that's pushing the universe to expand faster and faster, right?
Exactly. Imagine the universe is like a car that's not just cruising, but hitting the accelerator. And we're left wondering, where's the gas pedal? What's fueling this cosmic joyride? That's the enigma of dark energy.
Okay, I can visualize that. So where does this Tsallis model fit into the picture? Is it the missing gas pedal?
It's more like proposing a completely different type of engine altogether. You see, the simplest explanation we have for this cosmic acceleration is something called the cosmological constant. It's this idea that empty space itself, the vacuum, possesses energy.
Wait, so even the emptiest parts of the universe aren't actually empty? They've got this inherent energy that's pushing everything apart?
Yeah, pretty wild, right? But there are a few snags with this idea, and some are pretty significant. One of them is called the cosmic coincidence problem. Basically, it asks why the amount of dark energy we observe right now lines up so perfectly with the amount of matter in the universe.
So it's at this perfectly balanced cosmic scale, but instead of, feathers and bowling balls, it's this invisible energy and all the stuff we can actually see.
Exactly. And the odds of that happening randomly are, well, astronomically slim, to say the least. It makes you wonder if there's something else at play. Like maybe our understanding of gravity needs a bit of an update.
Okay, so we've got this massive cosmic puzzle on our hands. And the simplest explanation just isn't cutting it. What other explanations are physicists exploring?
Well, some are diving into modified gravity theories. It's basically saying, what if gravity behaves differently on those mind-bogglingly huge cosmic scales? Then there are scalar fields, these invisible energy fields thought to permeate space, potentially driving the expansion.
So lots of suspects in the lineup. But the paper you sent us goes down a completely different path. It explores something called holographic dark energy, or HDE for short.
Exactly. And this is where things get really interesting. HDE isn't about some new particle or mysterious force. It proposes that dark energy is an emergent property of the universe itself.
Emergent property? I mean, it's not really a thing, but more like a consequence of how the universe is structured. That's a pretty wild concept.
It really is. Think of it like this. Imagine the universe as a giant sphere, and we're stuck on the inside. HDE suggests that dark energy isn't something within the sphere. It's more like a property of the sphere's surface. It's a property of its boundary.
Okay, now my brain's starting to hurt, in a good way, of course. But that's what we're here for, right? To dive into the deep end and see what we can uncover.
Exactly. And that's where this Tsallis model comes in. It takes this holographic idea, this concept of dark energy being tethered to the universe's boundary, and throws in a fascinating twist.
And that twist, I'm guessing, is where things get even more interesting.
You could say that, because the Tsallis model is based on a fundamentally different way of looking at entropy. And that, my friend, changes everything. But we can delve into that a bit later.
Okay, so we're dealing with this crazy idea that dark energy isn't some thing hanging out in the universe, but it's more like a characteristic of the universe's edge. And then on top of that, we throw in this Tsallis model, which is changing how we even think about entropy itself. I'm hooked. Tell me more.
All right, let's break the Tsallis model down a bit. Imagine you're standing on the surface of that giant sphere we talked about. You remember that? You can't see forever, right? There's a limit.
Sorry, the horizon.
Exactly, you got it. But in cosmology, the kind of stuff we're talking about here, we have something called the future event horizon. It's kind of like the ultimate horizon, the absolute furthest point that light emitted today could ever reach us in the future. And that's even considering that the universe is always expanding.
Okay, so like the ultimate cosmic boundary, this horizon. How does the Tsallis model use that to explain dark energy, though? I'm ready for my mind to be blown here. Lay it on me.
Okay, so this is where it gets A bit technical, just a tad, but I think you can handle it. Stick with me. So, you know how entropy is usually thought of as like a measure of disorder?
Yeah, like my desk.
But it's not just about physical stuff. It's also related to information, believe it or not. The more information you need to describe something, the higher its entropy.
Okay, so more mass, more information, more entropy. Gotcha. But what does this have to do with the edge of the universe?
Well, that's the cool part. The Tsallis model says that the entropy of the entire universe, the whole shebang, isn't just about what's inside it, the stuff, It's also about how much information you could cram onto that boundary, onto that future event horizon we were just talking about.
So the universe is like, what, a giant hard drive with a storage limit? And that limit on how much information it can handle is somehow connected to dark energy? Seriously. This is wild.
You're getting it. That's a great way to think about it. Now, here's where the Tsallis part really comes into play.
Okay.
This model is named after a very smart physicist, Konstantinos Tsallis. He came up with this whole new way of calculating entropy.
New and improved, what's so different about his way of looking at it?
It all boils down to something called non-additivity.
Non-additivity. Okay, now you're just using big words to sound smart.
Haha, not at all.
Yeah.
It's actually pretty straightforward. Imagine you're mixing paint, right? You mix some blue and some yellow, and what do you get? You get green.
Everyone knows that.
Right,
Yeah.
because that's additive. But what if sometimes, just sometimes, you mix blue and yellow and got purple? That's not how it's supposed to work, right?
Right.
That's kind of what non-additivity is all about. Things don't always combine in the most predictable way,
So like the universe is mixing cosmic colors, and sometimes it throws us a curveball with the results.
Exactly. That's a great way to put it. And the Tsallis model, it takes this idea of non-additivity and applies it to the way entropy itself functions, but on that massive cosmic horizon.
So in the Tsallis model, how that boundary acts, how much information it can deal with, that's what's ultimately driving the acceleration of the universe.
Bingo. You got it. It's not some weird, mysterious force out there, but more like this, pressure, you could call it, from the universe's own information limit. And that pressure, that's what's pushing everything outwards.
Now, this paper you sent in, it doesn't just explain the Tsallis model, right? It actually looks at what happens when you apply this model to, the way galaxies and stuff evolve.
Exactly. Remember those perturbations we touched on earlier?
The little ripples in space-time.
Those are the ones. Well, this paper digs deep into how this Tsallis model actually affects how those perturbations grow, or maybe even shrink over, like, billions of years.
And I'm guessing this is where it gets really, really interesting, right?
Oh, absolutely. Because one of the biggest challenges for any model that tries to explain dark energy is, well, how can the universe be as stable and calm as we see it, If this invisible force is pushing everything apart so forcefully, and it's speeding up all the time, you'd think the universe would be a chaotic mess.
So we're picturing this universe, right, where dark energy is potentially this pressure from information itself, like hitting some kind of limit on the cosmic horizon, and that's pushing everything apart, making it expand. But then we've got these little ripples, these perturbations, and this paper is all about how those ripples behave with all this going on.
Exactly. And you'd think, right, that with all that dark energy pushing everything outwards, those perturbations would just get bigger and bigger.
Right. Like if you dropped, I don't know, food coloring into water, but the water is constantly being stirred, it would all just become this big, blurry mess.
Exactly. But that's not what we see when we look at the universe, is it?
Definitely not. We've got galaxies, we've got clusters of galaxies, all these structures. So those little ripples, those perturbations, they must have clumped together in some places, grown into these massive things we see.
You got it.
Okay, so how does this Tsallis model explain how those structures could actually form and stick around if dark energy is trying to smooth everything out?
Well, that's the crazy thing that they found. It turns out that with the Tsallis model, under certain specific conditions, you could actually have stable perturbations. They don't just blow up or vanish. They can actually hang around.
Hold on. So even though dark energy is doing its thing, pushing outwards, the way this model works, the way it thinks about entropy and information on that cosmic horizon, it creates some kind of counterbalance.
It's like this delicate balance.
Yeah.
Dark energy is there. It's pushing. But this whole entropy thing, the way it plays out in Tsallis, it allows for structures to exist. It's wild.
It's like the universe is having this epic tug of war with itself, and somehow stuff still manages to clump together. Now, there was something else in this paper that caught my eye. They were talking about different cutoffs. I think they used the term inverse Hubble parameter. What is that all about? Sounds a bit complicated.
It's not as bad as it sounds, honestly. Remember we were talking about the future event horizon earlier?
Yeah.
How that was important for this whole holographic dark energy idea?
Yeah.
Well, this inverse Hubble parameter, it's basically just another way to get a handle on the size of the universe, how fast it's expanding, all that.
So instead of looking at the edge of what we can see, they're using this Hubble thing to measure what exactly?
Think of it like measuring the universe's pulse, you know?
Okay.
The Hubble parameter, it tells us how fast the universe is expanding right now at this very moment.
Mm-hmm.
And if you flip that around, do a little math, you take its invert, you get a way to measure the universe's size.
So they're switching out one cosmic ruler for another. Did it change anything?
It did. That's the cool part. When they used this different cutoff, this Hubble thing, they actually got some really different results.
Different how?
Well, in some cases, you get this universe that just keeps expanding forever, faster and faster, even more extreme than what we see today. That's called a de Sitter state, if you want to get technical.
Okay, sure.
But they also found other situations, other scenarios, where the expansion actually chills out eventually, like it slows down. And that leads to a totally different story for how the universe ends up.
So just by changing how they're measuring things, the fate of the entire cosmos is different. That's kind of a big deal for a tiny equation.
It just shows how much we still don't know of this whole dark energy thing. There are so many possibilities, so many ways this could all play out. It's exciting.
I am definitely walking away with more questions than answers. We went from a mysterious force pushing the universe apart to talking about information at the edge of reality and now alternate ways to measure the universe. My brain is officially fried.
That's what we aim for. But hey, that's the beauty of cosmology, right? Every time we think we're getting close, the universe throws us a curveball. And that's what keeps us coming back for more.
Well, you've definitely convinced me to do some more reading on the Tsallis model and this whole holographic dark energy thing. Who knows, maybe it really is the key to cracking this whole dark energy code.
And even if it isn't, the journey is half the fun. There are so many more cosmic mysteries out there waiting to be discovered. Who knows what we'll find next?
All right, strap in because this deep dive, we're heading straight into like the biggest mystery of the universe, you know?
Oh, yeah.
Dark energy.
Right.
The thing that's like flinging everything apart faster and faster.
Yeah.
And you sent over this research about a model called Tsallis Holographic Dark Energy. I gotta say, I'm pretty excited to untangle this one.
Oh, it's a really cool area of research. It tries to deal with some of the really big questions that the more, traditional models like the cosmological constant kind of leave hanging.
So like why the universe is in such a hurry to grow, like what's powering this insane cosmic road trip?
Yeah, exactly. And this model, it suggests that it might be something, well, weirder, way more fundamental than we ever thought.
Okay, now you've got me hooked. But
Okay.
before we like disappear down the rabbit hole, let's start with the basics. What is Tsallis holographic dark energy? Really?
All right, well, it all starts with this super trippy idea, the holographic principle.
Yeah.
So imagine, right, that everything about our universe, everything we see, everything we know, it's all actually encoded like on a giant cosmic movie screen.
Hold on, are you saying our universe is just one giant hologram? Like something straight out of Star Wars?
Kind of. It's like, imagine a 3D movie projected from a flat screen. Now, you take that idea and you apply it to dark energy. And that's where this holographic dark energy HD key comes in. It says dark energy. It isn't some weird stuff filling space. But it's like it's a consequence of all this information crammed onto the universe's outer limits.
All right, I think I'm with you so far. But what about the Tsallis part? What makes this one different from regular HDE?
Okay, this is where it gets really wild. Tsallis HDE, it brings in this thing, it's called non-additivity. It's represented by the Greek letter gamma. You can think of it like a volume knob. It fine-tunes the relationship between entropy and the area of this giant cosmic screen.
Entropy. Okay, back up a second. We're talking like my sock drawer, always getting more chaotic, right? What does that have to do with dark energy?
You're actually closer than you think. Entropy, it's basically a way to measure disorder or randomness, right? And in a closed system, like, say, the entire universe, entropy, it can only go up. So picture this. You're applying this idea to the whole universe. The classic view is that entropy, it's like directly proportional to the area of the universe's boundary. Think like the event horizon of a black hole.
Right, the point of no return. Things get really weird once you cross that line.
Exactly. But here comes Tsallis saying, hold on a minute. What if that relationship, it's not so clean, especially at this scale? What if those quantum effects, those tiny rules that run the universe, mess with it all? That gamma's big entrance. It's there to account for those quantum quirks.
So Tsallis is basically saying, hey, maybe the universe doesn't play by our nice, neat rules, especially with something as bizarre as dark energy.
Exactly. It's about making our models more flexible. They've got to match the weirdness of the quantum world, right?
See, this is what I love about these deep dives. We're prying open like the guts of the universe, finding all these new cosmic gears and levers.
And trust me, it gets wilder. The research you sent, it dives into what happens to this model when you throw in perturbations.
Perturbation. Okay, now that sounds a little ominous. What are we talking about?
Imagine them like ripples, little fluctuations in the fabric of dark energy itself.
Yeah.
Like waves on that giant cosmic hologram we talked about.
Got it. But the universe is expanding all the time. Wouldn't you expect these ripples, these perturbations, to just keep growing, maybe even tear the whole model apart?
You'd think so, right? But Tsallis HDE, it throws us a curveball. The research actually found that depending on the value of that gamma we talked about, our quantum weirdness, dial those perturbations, they can actually just vanish, completely disappear, or just freeze in place.
Wait, seriously, they just poof, gone. That's wild. But what does that mean for the model itself? Is it a good thing?
This is the exciting part. Those vanishing perturbations, they hint that this model, this Tsallis HDE, it might be way more stable than we thought. Like it might just dodge those catastrophic meltdowns that plague other dark energy models.
It's like those cosmic ripples were a stress test, and instead of crashing and burning, it just absorbed them.
Exactly. And that's a big win for Tsallis HDE. It means it just might be able to explain the universe without, falling apart at the seams.
This is already mind-blowing, but I have a feeling we're just getting started, right?
Oh, definitely.
Yeah.
We've only scratched the surface of Tsallis holographic dark energy. There's so much more to uncover. Oh yeah, we've got a lot more to explore. Like the research, it doesn't stop at these ripples just disappearing. It also looks at what happens when we bring in another big player, regular matter.
Matter. I thought we were, ignoring that for now, sticking to the cosmic hologram and all that.
Well, in a perfect model, maybe. But we live in this messy, amazing universe with galaxies and stars and planets and all that stuff. It's made of matter. And matter, well, it brings gravity to the party.
Right. Gravity. Matter's big claim to fame. So how does adding matter into this whole thing change things for Tsallis HDE?
Think of it this way. Matter's gravity, it can tug on space-time, right? It can mess with those delicate dark energy ripples we've been talking about. And the research, it actually dives right into that. And it finds that, yep, matter's presence, it definitely throws its weight around, influences how those dark energy waves evolve.
So it's like we were studying ripples in a perfectly still pond, and then boom, someone jumps in, making a huge splash.
That's a great way to put it. And yeah, it definitely makes things more complicated. But the question is, does matter completely derail the Tsallis HDE model? Does it break it?
Does it? Does matter throw a wrench into our cosmic engine?
Not necessarily. Remember, what we're really interested in is the long-term behavior of these perturbations. Like, even if matter causes some initial wobbles, do those wobbles die down or do they spiral out of control? And what the researchers found is that even with matter messing around, there's still this whole range where those dark energy ripples, they either just vanish or they freeze up, just like we saw before.
Okay, so even with matter's gravitational shenanigans, Tsallis HDE is still standing strong. But I sense a but coming.
You know me too well. The researchers, they decided to really push things. They asked, what if dark energy and matter, what if they don't just coexist, but they actually interact, talk to each other?
Whoa, now we're going full on cosmic. I always thought dark energy was like this lone wolf just hanging out, interacting with gravity on a huge scale.
Yeah, that's what most people think, but there are some really wild theories out there. Some models say that on these massive fields, there might actually be this subtle energy exchange between dark energy and matter.
So they're in a cosmic dance-off, constantly pushing and pulling on each other.
Exactly. And the research, it actually looks at that possibility. They brought in a model for this interaction. And then they looked at how it might change those dark energy perturbations we keep talking about.
Okay, now I'm really hooked. What kind of interaction did they use and what did they find? Does it blow up our whole model?
They focused on a kind of interaction where the energy exchange, it's tied to the densities of matter and dark energy, and also the Hubble parameter.
Okay, quick refresher. The Hubble parameter, that's like the speedometer of the universe, right?
Yeah.
It tells us how fast it's expanding right now.
Bingo. So, in this model, the more matter and dark energy you have, and the faster the universe expands, the stronger this interaction gets. It's like adding fuel to a cosmic fire.
Whoa, that sounds intense. What does that do to our poor little model's stability?
This is where it gets really cool. Even with this interaction, the results were surprisingly similar to when there wasn't any interaction.
Wait, seriously, this whole interaction thing doesn't just destroy the Tsallis HDE model.
It seems like for certain values of those key parameters, those dark energy perturbations, they still manage to chill out. Like they find this cosmic balance where this particular type of interaction doesn't make everything go haywire.
So Tsallis HDE survives another round in the cosmic boxing ring, but I have a feeling there's one last challenge waiting for us out there on the edge of the universe.
You're reading my mind. Remember when we talked about the cutoff? That boundary that defines the scale of holographic dark energy?
Vaguely. It's like trying to remember a dream. Refresh my memory.
Right.
The boundary where all that holographic information is encoded. But we were using the event horizon of a black hole as our example, right?
Exactly. It's a natural choice since the event horizon is this well-defined boundary beyond which information is lost to an outside observer. But the research also briefly explores a tantalizing what if. What if, instead of the event horizon, we use the Hubble horizon as the cutoff for our holographic principle?
Now we're really going deep. The Hubble horizon is the edge of what we can observe, right? Because beyond that point, galaxies are moving away from us faster than the speed of light.
You nailed it. And what the research suggests is that, depending on this cutoff point, the long-term behavior of Tsallis HDE, and by extension, the universe itself could be dramatically different.
Okay, now I'm really intrigued. What kind of differences are we talking about here? Does the universe still expand forever if we use this Hubble horizon cutoff?
That's the million-dollar question. The research found that if we use the Hubble horizon as the cutoff, we could end up in a universe where dark energy still dominates. But instead of expanding at an ever-increasing rate, the expansion eventually slows down and approaches a constant value.
So instead of a runaway cosmic joyride, it's more like we eventually hit cruise control.
Precisely. And in this scenario, those pesky perturbations we've been talking about either vanish completely or decay over time, depending on the value of that gamma parameter.
Gamma, gamma, gamma. It really is the key to unlocking all these cosmic mysteries. But I have a feeling things can't be that straightforward. Does using the Hubble horizon introduce any new wrinkles?
It wouldn't be cosmology without a few unexpected plot twists. The research acknowledges that for certain values of gamma, those perturbations might refuse to settle down, potentially creating problems for the stability of the Tsallis HDE model with a Hubble horizon cutoff.
So even though Tsallis HDE seems promising, it's not a done deal. There are still unanswered questions and different paths to explore.
Absolutely, and that's what makes this area of research so captivating. It's like we're standing at a crossroads, with different models offering glimpses into possible cosmic futures.
It's both exhilarating and a little humbling, isn't it? Realizing how much we still don't know about the universe and its ultimate fate.
It certainly keeps us on our toes. But that's the beauty of science. It's a process of constant exploration and discovery, always pushing the boundaries of our understanding.
Speaking of pushing boundaries, we've covered a lot of ground in this deep dive. We've journeyed from the mind-bending realm of the holographic principle to the perplexing nature of dark energy, and we even explored different scenarios for the universe's expansion. What are some key takeaways you hope our listener walks away with?
I think the biggest takeaway is that dark energy might not be this static, unchanging force, but rather a dynamic phenomenon deeply intertwined with the fabric of space-time itself.
Right. This whole concept of holographic dark energy, it's like the universe is a giant puzzle box, and we're just starting to find the hidden compartments.
Exactly. And within that puzzle box, models like Tsallis holographic dark energy are attempting to explain the observed acceleration of the universe's expansion in a way that incorporates these mind-blowing concepts.
And what's remarkable is that Tsallis HDE has managed to hold its own, even when we throw in the curveballs of matter's influence, potential interactions between dark energy and matter, and even changing our fundamental assumptions about the cutoff scale for the holographic principle.
Absolutely. It underscores that this model has some intriguing features that warrant further investigation. But like any scientific theory, it requires rigorous testing, observation, and refinement.
Because as we've seen today, when it comes to cosmology, there's always another layer to uncover, another mystery waiting to be unraveled.
Precisely. And that's what makes this field so endlessly fascinating.
It's been an incredible journey into the heart of these cosmic mysteries. So for anyone listening who's ever looked up at the night sky and felt a sense of awe and wonder, remember the universe is full of surprises, and the quest to understand it is just beginning. Thanks for joining us for another deep dive. Until next time, keep those minds curious.
All right, so get ready to stretch your brain, because today we're diving into a cosmic enigma that'll really make you think. Tsallis Holographic Dark Energy, or THDE for short.
Wow, yeah.
You sent over some seriously intense research on this, and honestly, I'm a little nervous, but mostly excited to unpack it all.
Yeah, it's going to be a good one.
But before we get lost in the weeds of THDE, let's start with something everyone knows: cake.
Okay.
Imagine the universe is like a cake baking in the oven, right? All those ingredients, the stars, planets, galaxies, those are all mixed up, ready to go. We can see them, we can study them.
Right.
But here's the thing. This cosmic cake, it's rising way faster than our understanding of those ingredients should allow. Something unseen is at work here. Something's pushing everything apart.
It's true.
And that, my friend, is dark energy.
Yeah.
And this THDE model is an attempt to explain what that mysterious force might be.
Yeah, and what's really fascinating about THDE is that it takes a completely different approach compared to, those more traditional models.
Okay.
It throws in this thing called the non-additivity parameter.
Oh, boy.
Which is represented by the Greek letter gamma, or like goth.
Okay.
And essentially it suggests that the usual rules that we use to describe how disordered a system is, that's like entropy, which I'm sure many of your listeners are familiar with.
Right.
It suggests that those rules might need a little bit of a tweak when we're thinking about the very, very edge of the universe.
Okay, so we're already talking about entropy and the universe's edge. I can feel my brain starting to hurt a little bit.
Yeah.
But before we go too far, how did we even discover dark energy in the first place?
Right.
Because it's not like we can just point a telescope at it and be like, aha,
Yeah.
there it is.
Well, you're right. You can't see it. It's not like a thing. It was actually through observing something much more tangible, exploding stars or supernovae.
Okay.
So back in 1998, these astronomers were studying these distant supernovae and noticed something very peculiar. The universe's expansion, it wasn't constant. It was actually speeding up.
No.
Yeah, it was kind of like finding out our cake is rising faster and faster as it bakes.
Right.
And this was a major head scratcher because, the prevailing theory at the time was something called the Standard Model of Cosmology, and that relied on this thing called the cosmological constant, which is often represented by the Greek letter lambda, or s.
Okay.
And this basically acted like a constant energy density throughout space. The problem was that the acceleration observed didn't line up with what this constant suggested at all.
So using this cosmological constant, this wasn't quite working out. Why not just stick with that model? Was it just not explaining this acceleration, or were there deeper issues?
It wasn't just about the acceleration itself, although that was a major clue. The standard model, which we often refer to as the CDM model, ran into some pretty big theoretical hurdles.
Like what?
Well, for one, the actual measured value of the cosmological constant was way, way smaller than what our understanding of quantum physics would predict. We're talking many orders of magnitude smaller. This became known as the smallness problem.
Okay.
And then on top of that, there was the cosmic coincidence problem.
Which is?
Why is the density of this unseen dark energy, the thing that's driving the universe's acceleration, why is it so darn close to the density of all the matter in the universe right now? It's like these two things, dark energy and matter, which seem totally unrelated, just happen to be at similar densities at this point in the universe's history. Talk about a coincidence?
Yeah, that's not just a red flag. That's a whole parade of red
Yeah,
flags.
pretty much.
So if sticking with the standard model wasn't going to cut it, what other explanations were physicists tossing around for dark energy?
Oh, so many. They explored all sorts of wild ideas.
Like what? Give me some examples.
Well, one was this idea of quintessence, imagining dark energy as this field that changes over time, unlike the constant we'd assumed before.
Okay.
Then there was phantom energy.
Oh, spooky.
And this one gets a little spooky because it suggested that the universe could actually be ripped apart in a big rip.
Okay, suddenly feeling a little less enthusiastic about this whole dark energy thing. What else?
Well, some physicists even started looking at modified gravity theories, wondering if maybe, just maybe, our understanding of gravity itself needed an overhaul
Interesting.
when thinking about these cosmic scales. So yeah, lots of head scratching and brainstorming. But amidst all of this, there was another, even more radical idea brewing, the holographic principle.
Okay.
And that's where THDE comes in.
Okay, this holographic principle, this sounds intriguing. How does it attempt to tackle this dark energy conundrum?
Well, imagine a hologram, one of those 3D images encoded on a 2D surface. The holographic principle takes that idea and applies it to the entire universe.
Whoa.
It suggests that all the information about our 3D universe might actually be encoded on its 2D boundary, kind of like a cosmic projection. And this is where things get really mind-bending.
So instead of trying to figure out what's inside the universe, like what's causing it to accelerate, this holographic principle says we need to look at its edges.
Exactly. It's a pretty radical shift in thinking.
It really is.
And THDE takes this idea and runs with it, bringing in this concept of Tsallis entropy.
Okay.
Think about shuffling a deck of cards, right?
Okay.
Entropy, in simple terms, it measures how disordered those cards are.
Okay.
Tsallis entropy suggests that those rules of shuffling, they might work a little differently at those cosmic edges we were talking about.
Okay, I think I see how these pieces are starting to fit together.
Yeah.
But we're dealing with some seriously abstract stuff here. Like, there are equations involved, right?
Right.
I always get a little intimidated by equations.
There are. Don't worry. I promise to keep things as painless as possible. The core equation for THDE is actually surprisingly elegant. Rho 3CPO L42.
Okay.
Now, rho, that just represents the density of dark energy. C is a constant.
Okay.
Although its exact value is something physicists are still trying to nail down.
Of course.
But the really juicy parts of this equation are L and that gore.
All right, walk me through it. What do those juicy parts represent?
Right, so L, that relates to the size of the universe.
Okay.
But here's the catch. There are different ways to define just how big the universe is.
Okay.
The research you shared actually explores a couple of possibilities. The event horizon, which is kind of like the edge of the observable universe,
right,
beyond which light hasn't had time to reach us yet.
Right.
And then there's the Hubble horizon, which relates to how far we can see back in time.
So depending on how we define the universe's size, our L value changes, and that in turn affects the whole equation.
You got it. And then there's Gauss, our non-additivity parameter.
Right.
Which is like a tuning knob for how entropy behaves at those cosmic boundaries. So by adjusting L and algo, THDE might actually be able to solve some of those pesky problems that traditional cosmological models, like that CDM model we talked about, just can't quite crack.
This THDE model is starting to sound like a serious contender in the cosmic sweepstakes.
Yeah.
But how do we even go about studying something like this? It's not like we could just, like, hop in a spaceship and take measurements at the edge of the universe.
You're telling me this is where things get even more interesting.
Okay.
Instead of thinking of dark energy as some kind of exotic fluid that's filling space, THDE suggests we look at how the universe's boundary itself fluctuates, kind of like ripples on a pond.
Okay.
These fluctuations are called perturbations, and they act like little clues left behind by dark energy.
So these perturbations are key to understanding how THDE actually works in the universe.
They are.
But how do we track these cosmic ripples?
That's where the math comes in. But don't worry, I'll decode it for us.
Good.
We have this really important equation. It's equation 10 from your research that describes how these perturbations evolve. Epstic FDHH 3, it was like 3 Hace plus dem.
Okay.
Now, I know this looks like a jumbled mess of symbols, but bear with me.
Okay, I'm ready. Decode away.
I represents those perturbations, those ripples we're interested in.
Okay.
H is the Hubble parameter, which, to keep things simple, tells us how fast the universe is expanding at any given moment.
Right.
And Dodd and Dom, they represent changes in the density of dark energy and matter, respectively.
Okay.
So this equation is basically describing how those ripples on the universe's boundary are affected by the presence of dark energy and matter.
Okay, so far so good.
Yeah.
What have researchers discovered by studying this equation? What do these ripples tell us about dark energy?
This is where things get really wild.
Yeah.
They've found that for certain values of H, that non-additivity parameter, and C, that constant we talked about earlier, these perturbations, they don't just grow out of control,
Right.
as you might expect in an expanding universe, right?
Right.
Instead, they can actually freeze,
Freeze.
meaning they stop growing, or even completely vanish over time.
Wait, these ripples on the universe's boundary can just disappear.
It's pretty amazing.
That's incredible. What does that even mean for the universe?
It's a huge deal, and it has major implications for the universe's stability. Remember those alternative dark energy models that led to the universe ripping itself apart in a big rip?
Yeah.
Well, THD, with the right combination of Wa and C, might offer a much more stable alternative.
Okay, now you've really got my attention. A stable universe sounds much more appealing than a cosmic rip.
Uh-huh.
But there's a catch, isn't there? You mentioned earlier that there are different ways to define the universe's size, right?
You've got a sharp memory. You're right. These findings, whether those perturbations freeze or vanish, they actually depend on which definition of the universe's size, the event horizon or the Hubble horizon that we plug into our equations.
Okay.
Each choice leads to a different set of predictions about how those perturbations behave.
So which is it? The event horizon or the Hubble horizon? Which one gives us the most accurate picture of how THDE works?
That's the million-dollar question. The research you shared, it explores both possibilities, and honestly, each one is fascinating in its own right. But there's another layer of complexity we need to add into the mix. Matter.
Hold on. I thought dark energy was the big cheese, the dominant force driving the universe's expansion. Does matter really make that much of a difference?
It does. Even though dark energy is calling the shots on a cosmic scale, matter still plays a role.
Okay.
Those initial calculations we discussed, they focused on a universe dominated by dark energy. But for a truly accurate picture, we need to factor in how matter's influence on those perturbations changes things over time.
So we can't just focus on this mysterious universe-stretching power of dark energy. We also need to account for all the regular stuff out there.
Yeah.
All the stars and galaxies and planets.
Exactly. And the math gets a bit trickier here, but the payoff is worth it. We have to bring in a couple more equations 15 and 16 from your research. These build on that earlier equation we discussed, the one with all those symbols, to incorporate how matter density fluctuations represented by affect the overall picture. Think of it like this. We're adding another layer of ripples to our cosmic pond, this time caused by the clumping of matter throughout the universe.
Okay, so we're taking those initial ripples caused by dark energy, and now we're adding in the ripples caused by matter.
Right.
That sounds incredibly complex.
It is.
What's the takeaway from adding this extra layer of detail?
Researchers found something truly fascinating by studying these equations. They discovered that the way those perturbations behave in the very distant past, when the universe was much smaller and matter was even more dominant, can actually offer clues about how they might behave in the distant future.
Whoa. Hold on. You're saying that by looking back in time, we might be able to predict the future of dark energy and these perturbations? It's like cosmic time travel.
In a way, it is. It's like those patterns we see in the cosmic microwave background radiation, the afterglow of the Big Bang.
Right.
Those patterns tell us about the universe's earliest moments, but they also hold clues about its ultimate fate. Similarly, the behavior of those perturbations in the early universe, when influenced by both dark energy and matter, might give us a glimpse into the future evolution of the cosmos. And you know what's really cool? The research suggests that by accounting for matter, we see that those perturbations, those ripples, they don't necessarily have to keep growing forever. There's a good chance they might eventually settle into a stable state. And that has huge implications for the long-term fate of our universe.
A stable universe where those perturbations eventually settle down.
Yeah.
That's a much more comforting thought than some of the other alternatives we've discussed.
Right.
But you did mention there's another way to define the universe's size. We talked about the event horizon, but there was another option.
You're right. We've been mainly focusing on the event horizon as our cosmic measuring stick for THDE.
Right.
But the research also dives into another really interesting possibility, using the inverse Hubble parameter, which is denoted as H1.
Okay, quick refresher. The Hubble parameter, that tells us how fast the universe is expanding, right?
It does.
So what exactly does its inverse, this H1, represent in this context?
Essentially, when we use H1 as a measure of the universe's size, we're looking at how far light can travel and the time it takes for the universe's expansion to double. It's another way of grappling with the vastness of the cosmos.
So instead of using the event horizon, the edge of the observable universe, we're using the model when we make that switch.
Hold on tight, because this is where things get really interesting.
Okay.
The research introduces equation 23, which specifically describes how those all-important perturbations in dark energy density behave when we use the inverse Hubble parameter. And you want to know the kicker?
Yes.
This equation reveals two incredibly intriguing possibilities for the universe's ultimate fate.
All right, lay it on me. What does the future hold if we use the inverse Hubble parameter to understand THDE?
Okay, so the first possibility is that the Hubble parameter, that cosmic speedometer we talked about, eventually settles into a constant value.
Okay,
We represent this as h-const.
got it.
In this scenario, the universe would enter what's called a de Sitter-like phase, where it expands at a steady rate forever.
Okay.
However, what happens to those perturbations in this de Sitter-like universe? That's where things get even more complex. Their fate actually depends heavily on the value of our friend psi, the non-additivity parameter.
So our old pal Kant psi is back to shake things up again.
Well,
What about the second possibility? What happens if the Hubble parameter doesn't settle into a constant value?
the second possibility is even wilder. It suggests that the Hubble parameter could actually approach zero over time,
Really?
which we denote as HA.
Okay.
In this scenario, the universe's expansion would gradually slow down, like a car running out of gas, until it eventually came to a standstill.
Wow.
And what about those perturbations under these conditions?
Yeah.
The research suggests they would eventually fade away entirely.
Wow. So we have two dramatically different potential outcomes. Either a universe that keeps expanding forever, with the fate of those perturbations hanging in the balance,
Right.
or a universe where expansion just grinds to a halt and those perturbations disappear.
Yeah,
It's like the cosmos is at a crossroads.
exactly. And here's the most exciting part. By studying how those perturbations behave in each of these scenarios, we might be able to figure out which explanation for the universe's expansion and dark energy is the most accurate. It's like each model leaves its own unique fingerprint on those cosmic ripples.
This is all incredibly mind-blowing stuff. We've covered a lot of ground, from the holographic principle and Tsallis entropy to the potential for a stable universe,
Right.
or one that keeps expanding forever. But before we get ahead of ourselves, there's one more piece of the puzzle we need to unpack.
Okay.
And this one takes us even deeper into this weird and wonderful world of THDE. So what is it? What's this final piece of the puzzle?
Yeah.
What else can these perturbations tell us about the universe and this whole idea of Tsallis holographic dark energy?
Well, we've been talking about how these perturbations in space-time can either freeze, meaning they stop growing, or completely vanish, right?
And we touched on how this is related to the values of OGO, that non-additivity parameter that makes THDE so unique.
Exactly. And this is where it gets really mind-blowing. What the researchers found is that there's a very specific mathematical link between the behavior of these perturbations, whether they freeze or vanish, and the value of OG.
Okay, so the fate of these perturbations is directly tied to OG. But what's the big deal? Why is this relationship so important for understanding the universe?
Because it suggests that O might be one of the keys to the universe, having structure at all galaxies, clusters, the whole cosmic web. For certain values of O, specifically when it's less than 1, those perturbations tend to freeze. That might sound uneventful, but it's actually crucial for the universe as we know it.
Why is that? What happens when those perturbations freeze?
When they freeze, they don't just disappear. Instead, they provide a sort of scaffolding. They create regions of slightly higher density in the universe, places where matter can clump together over billions of years thanks to gravity.
So you're saying these tiny quantum fluctuations we've been calling perturbations are actually the seeds of galaxies, that without them, the universe might just be a vast homogeneous expanse.
That's the idea. It's like the universe needs these little wrinkles in space-time to create anything interesting. And here's where the value of Ga gets even more crucial. For other values, particularly when Ga is greater than 1, something completely different happens. Those perturbations, they don't just freeze, they actually vanish over time.
Wait, completely vanish? Poof, gone. What kind of universe would we have if those perturbations just disappeared?
It's a fascinating question, and one that researchers are still trying to understand fully, but one possibility is that in a universe where perturbations vanish, large-scale structure, it might never really form. We might end up with a universe that's, well, smooth, homogeneous, a cosmic void, without those glorious galaxies we're used to.
So depending on this one parameter, we could have a universe teeming with galaxies, stars, planets, even life, or a universe that's essentially empty. That's a pretty significant consequence to hang on one variable. It's like a cosmic light switch is either flipped to galaxies on or galaxies off.
It's a powerful image. And it highlights just how deep this research into THDE goes. By trying to understand this model, by unraveling the mysteries of dark energy, we're not just refining our picture of an expanding universe, we're potentially glimpsing the very mechanisms that determine whether the universe is a fertile ground for complexity or a vast, sterile expanse.
It's incredible to think that such a seemingly abstract concept, this non-additivity parameter goal, could have such profound implications for the universe we live in.
It really is. Makes you wonder, what if there are other hidden variables, other fundamental constants out there that we haven't even begun to consider, subtly shaping the cosmos in ways we can't yet imagine?
It's both exhilarating and a bit humbling, isn't it? To think that we're just scratching the surface of understanding the universe and all its wonders.
Absolutely. But that's what makes cosmology so captivating. There's always another mystery to unravel, another layer to peel back. We've learned so much about the universe, but there's still so much more to discover. And who knows what incredible new insights await us just beyond the horizon of our current understanding.
Well, on that note, I think we've reached the end of our deep dive for today. A huge thank you to you for guiding us through the complexities of Tsallis holographic dark energy and for leaving us with even more questions than we started with. To our listeners, thank you for joining us on this incredible journey into the depths of the cosmos. Until next time, keep looking up and keep asking those big, beautiful questions about the universe around us. Hey there, knowledge seeker. Ready to dive into the mind-bending world of cosmology?
This research delves into a new model for dark energy, a mysterious force driving the universe's expansion.
Okay, let's unpack this. Imagine a balloon with coins taped to it. Those coins represent matter in the universe. When you blow up the balloon, you'd expect the coins to spread out slower and slower as the balloon gets bigger, right?
Exactly. The standard model, CDM, relies on the cosmological constant, which represents a kind of vacuum energy in the universe.
So what does this all mean? Scientists are looking for alternative explanations for dark energy, and that's where holographic dark energy, HDE, comes in.
This is where the concept of holographic dark energy gets truly intriguing. We can think of it as the information content of the universe, encoded on this boundary.
But here's the catch. The classic HDE model had a problem. It seemed initially unstable. It predicted a negative sound speed, which means any small disturbance would quickly grow out of control, leading to chaos in the universe. Absolutely. And this is where the Tsallis holographic dark energy, THDE model, enters the picture. It's a more sophisticated model based on a modified entropy area relation, a connection between the amount of information and the area of a region in spacetime.
So we have this new model, THDE, trying to explain dark energy and fix the stability issue. It's starting to sound pretty promising, but I have a question. How do we even know if this model is working? What are scientists looking for to prove or disprove it?
That's a great question, and it gets to the heart of why this research is so important. Stability is crucial for any dark energy model because we don't want a universe that's constantly on the verge of collapse.
Imagine that balloon I mentioned earlier, but it's inflating so fast that it pops. Not a good outcome for our universe. So to test these models, physicists look for perturbations, fluctuations in the fabric of spacetime. Perturbations. Sounds like a recipe for a sci-fi movie, but I get it. It's like ripples in a pond, but instead of water, it's the very fabric of spacetime. And these ripples are caused by variations in dark energy density, right?
Right. Think of it like this. If dark energy is a smooth, uniform force, then these perturbations are tiny deviations from that smooth flow. They're like tiny waves in the cosmic sea. And the way these perturbations evolve over time tells us a lot about the stability of the model.
So what did the researchers in this paper find out about perturbations in the THDE model? Did they get rid of those pesky universe-collapsing ripples?
Here's where it gets really interesting. The researchers took a different approach to analyzing perturbations. Instead of just treating dark energy as a fluid, they considered how perturbations affect the future event horizon itself. Remember, the horizon is key to the HDE model, and it's a bit more complex than just a simple fluid. And their calculations showed something really fascinating.
Spill the beans. What's so fascinating about these calculations? What did they find out about the future event horizon and the stability of the THDE model?
They discovered that for certain values of DEC, the non-additivity parameter we discussed earlier, and a parameter called C, the perturbations of the event horizon actually vanish or freeze over time. This suggests that the THDE model might lead to a stable universe where those ripples don't grow out of control. That's a big deal.
Wow, that's pretty mind-blowing. So are we good to go then? Is this the end of the dark energy mystery?
Not so fast. While the results are promising, the researchers didn't stop there. They want to see how those perturbations behave in a realistic universe where matter, the stuff we can actually see, is also present.
Makes sense. We're not just living in a dark energy bubble, right? There's all that matter out there too. So how did they account for that in their calculations?
They factored in matter perturbations, which are fluctuations in the density of matter throughout the universe. This is a crucial step because it turns out that matter perturbations can significantly influence the evolution of those space-time ripples.
Whoa, hold on a second. So matter is influencing dark energy perturbations. That's a big deal. I mean, we're used to thinking about these two things as separate entities, but this research suggests that they're not so independent after all.
Exactly. We're used to thinking about dark energy as this mysterious force that's driving the expansion of the universe, and matter as the stuff that makes up everything we see, like stars, planets, and us. But this paper highlights how those two aspects are interconnected.
And what did they find out about the interplay between these two forces? Did those matter perturbations help stabilize things or make the ripples even more unstable?
Their calculations showed that even when accounting for matter, the fluctuations in the THDE model still tended to freeze over time for many parameter values. This reinforced the idea that THDE could lead to a stable universe. And it turns out that the way matter perturbations affect these spacetime ripples is sensitive to a specific model parameter called alpha, represented by the Greek letter A.
Wait, so we have a parameter called gamma, which is related to the entropy-area relation, and now we're introducing another parameter called alpha. This is getting complex.
It's important to remember that these models are built on mathematical frameworks, and they involve various parameters that we're still trying to understand. Alpha, in this case, dictates the nature of the interaction between dark energy and matter. A negative value of IY leads to less matter perturbation growth, which is quite interesting.
So we're finding subtle but potentially important details about this complex dance between dark energy and matter. But we're not done yet, are we? There's more to explore, right?
That's right. In the paper, the researchers also explored another variation of the model, this time using the inverse Hubble parameter, H1, as the cutoff scale instead of the event horizon. Think of it like a different lens through which we're viewing this holographic picture of the universe.
The Hubble parameter, isn't that related to the expansion rate of the universe?
Exactly. And by considering the inverse of the Hubble parameter, they were looking at different ways the universe could evolve in the future. They found two possible cosmological evolutions. One where the Hubble parameter approaches a constant, leading to a de Sitter regime where the universe expands exponentially, and another where the expansion slows down significantly.
So we're getting into some pretty deep cosmological territory here. And what about the stability of these models with the inverse Hubble parameter as the cutoff? What did they find out?
In the de Sitter scenario, where the expansion is constant, they found that perturbations only decay if our beloved non-additivity parameter, is greater than 1. That suggests potential instability for values of less than 1. But in the scenario where the expansion slows down, they found that perturbations always decay, suggesting stability.
Okay, so we have different models, different cutoffs, and different conditions that can lead to stable or unstable universes. This is getting complex, but it's also fascinating. I can't wait to see what these researchers do next.
And that's the beauty of scientific exploration. We're constantly learning and refining our understanding. But let's step back for a moment and think about the bigger picture. We've explored a complex model that tries to explain dark energy, and we've uncovered some fascinating implications for the stability of the universe.
We've learned about how matter can influence dark energy perturbations, and we've seen that different choices of cutoffs can lead to different cosmological evolutions.
But this model, though promising, still relies on abstract parameters. The real excitement lies in connecting it to observational data. If we can find evidence for specific values of Gu or C, those parameters we discussed, it could revolutionize our understanding of dark energy and the fate of our universe.
So think about it, listener. We're at the cusp of a new era in cosmology, where we might finally gain a deeper understanding of this mysterious force that's shaping our universe. It's like we're finally starting to see a clearer picture of the cosmos, one ripple at a time. And who knows what else we'll discover along the way. Thanks for joining us on this deep dive. The Hubble parameter, isn't that related to the expansion rate of the universe?
Exactly. And by considering the inverse of the Hubble parameter, they were looking at different ways the universe could evolve in the future. They found two possible cosmological evolutions. One where the Hubble parameter approaches a constant, leading to a de Sitter regime where the universe expands exponentially, and another where the expansion slows down significantly.
So we're getting into some pretty deep cosmological territory here. And what about the stability of these models with the inverse Hubble parameter as the cutoff? What did they find out?
In the de Sitter scenario, where the expansion is constant, they found that perturbations only decay if Cock, our beloved non-additivity parameter, is greater than 1. That suggests potential instability for values of Cock less than 1. But in the scenario where the expansion slows down, they found that perturbations always decay, suggesting stability.
Okay, so we have different models, different cutoffs, and different conditions that can lead to stable or unstable universes. This is getting complex, but it's also fascinating. I can't wait to see what these researchers do next.
And that's the beauty of scientific exploration. We're constantly learning and refining our understanding. But let's step back for a moment and think about the bigger picture. We've explored a complex model that tries to explain dark energy, and we've uncovered some fascinating implications for the stability of the universe.
We've learned about how matter can influence dark energy perturbations, and we've seen that different choices of cutoffs can lead to different cosmological evolutions.
But this model, though promising, still relies on abstract parameters. The real excitement lies in connecting it to observational data. If we can find evidence for specific values of bet or C, those parameters we discussed, it could revolutionize our understanding of dark energy and the fate of our universe.
So think about it, listener. We're at the cusp of a new era in cosmology where we might finally gain a deeper understanding of this mysterious force that's shaping our universe. It's like we're finally starting to see a clearer picture of the cosmos, one ripple at a time. And who knows what else we'll discover along the way. Thanks for joining us on this deep dive. All right, so today we're going deep, like deep into the cosmos. We're talking about dark energy, which, if you think about it,
It's the big one.
it's kind of wild. It's like the universe decided to hit the gas pedal billions of years ago, and no one knows what's fueling the engine.
Yeah, exactly. And it's not just driving like a normal car. It's more like pushing a car that's already going super fast to go even faster.
Yeah.
It's acceleration on top of expansion.
Precisely. It's like gravity took an extended vacation or something. And to try to make sense of it all, we're diving into this paper,
Lay it on me.
Evolution of Perturbations in the Model of Tsallis Holographic Dark Energy. Catchy, right? But it's by Artyom V. Astashenok and Alexander S. Tepliakov from the Kant Baltic Federal University. And they're looking at dark energy in a totally new way, like literally a new light.
It's a fascinating approach. They're suggesting that, well, maybe dark energy isn't some kind of exotic particle or a hidden force field. What if, and this is where it gets wild, what if it's like woven into the very fabric of the universe, like it's an emergent property of something even more fundamental?
Okay, before we get too far into the theoretical weeds here,
Right.
let's rewind for a sec. Back in 1998, do you remember this?
Oh, I do.
Astronomers made this huge discovery.
Yeah.
The universe's expansion, it's not slowing down, it's speeding up.
It was a bombshell, like completely flipped the script on everything we thought we knew about cosmology.
It's like finding out the Earth is actually flat. Wait, no, bad example. But you get the idea. It was a paradigm shift.
Totally. Before that, the common wisdom was that gravity would eventually win the tug of war, slow everything down, maybe even lead to a big crunch. But nope, the universe had other plans.
Exactly. And that's where dark energy comes in.
Our invisible friend.
The mysterious force that's making up, like, the majority of the universe's energy budget, counteracting gravity and driving that crazy expansion.
And the thing is, our current best model, this ACDM model, it tries to explain it with this thing called the cosmological constant.
Right.
But it's messy.
It's messy.
Like trying to fit a square peg into a round hole, it doesn't quite work perfectly.
Math doesn't quite add up, right?
Exactly. The values we're getting from quantum physics for what that constant should be, way off, like not even close. Plus, there's the whole cosmic coincidence problem. Why is there so much dark energy, and why does it seem so perfectly calibrated to allow for, well, us?
Right.
Stars, galaxies, life as we know it. It all seems a bit too convenient, doesn't it?
It's a head scratcher for sure.
So, naturally, scientists have been searching for other explanations.
Makes sense.
We've got quintessence, this idea of a field that changes over time, always evolving. Then there's the phantom model, But that one, well, it suggests the universe might rip itself apart eventually.
Yeah, the big rip. Not my favorite scenario.
Bit dramatic, isn't it?
It's a tad. Okay, so we've got these other ideas floating around, but they all have their own issues. So where does holographic dark energy fit in?
Well, that's where things get really interesting. See, HDE takes a totally different route, one that's rooted in this mind-bending concept from theoretical physics, the holographic principle.
Okay, now we're talking. This is where we transition from, like, regular astrophysics to something straight out of a sci-fi movie, right?
But think of it like this.
All right.
You know how a hologram works?
Yeah.
You have a flat two-dimensional surface, but it can project this whole complex three-dimensional image.
Right. Right.
Well, the holographic principle suggests that maybe our universe is doing something similar.
What?
Yeah, like what if all the information inside a region of space is actually encoded on the boundary of that region?
So you're saying our 3D reality is like a projection from a 2D surface at the edge of, well, everything.
It's such a wild idea.
That's more than that's like next level existential.
It is. But in this framework, dark energy isn't some mysterious stuff that's just hanging out, filling up space. It's more like an emergent property, a consequence of how information is organized on the universe's screen, so to speak.
Okay, I think I'm starting to get why you find this so fascinating.
Right. It's a whole new way of thinking about reality.
We're going to need a bigger blackboard for this one. But hold on, folks. Before my brain melts down from too much mind-bending awesomeness, we need to take a quick break.
When we come back, we're going even deeper. We'll unpack this idea of Tsallis holographic dark energy, or THDE, and explore how it might just rewrite our understanding of the universe's destiny.
All right, so we're back and ready to untangle this whole Tsallis holographic dark energy thing.
THDE, it's a mouthful, I know.
It is. But you mentioned it's a twist on the original holographic dark energy idea.
Right, so it all starts with this physicist, Constantino Tsallis.
Okay.
He came up with this, well, a new way of calculating entropy.
Entropy as in, like, a measure of disorder in the universe.
Exactly. But his way of calculating it, it's especially interesting when you're dealing with, the really weird stuff like black holes.
Black holes and entropy, two of my favorite cosmic mysteries. So how does Tsallis's idea play into all of this?
Well, in THDE, there's this really important piece of the puzzle called the infrared cutoff.
Infrared cutoff.
It sounds intense.
It's represented by L0, and basically it's like setting the scale for this whole holographic principle.
So like zooming in or out on the hologram.
Kind of. Imagine you're trying to figure out the size of the stage where this whole cosmic play is happening. That's what the infrared cutoff is trying to do.
Okay, I think I'm following. So how do you choose the right stage size for something as mind-boggling as the universe?
Great question. The paper actually explores three main contenders for this L0.
All right, let's hear them. What's option number one?
The most straightforward is the Hubble horizon. It's essentially the edge of the observable universe, as far as we can see right now.
Right, because the speed of light isn't infinite.
Exactly. It's like our cosmic horizon. Okay, makes sense. What's next?
Next up, we have the particle horizon. Think of it as the boundary of everything that could have, in principle, had a chance to influence us since the Big Bang.
So it's based on the universe's age, the ultimate limit of cause and effect for us.
Precisely. It gets pretty deep, pretty fast.
You're telling me. All right, what's the third contender?
Last but not least, we have the future event horizon. And as you might guess, this one's all about the future.
Oh, this sounds intriguing. Lay it on me. What's the future event horizon all about?
So because the universe is expanding and expanding faster all the time,
Right.
there's a point out there, a boundary, beyond which even light emitted today will never reach us.
Wow, that's kind of a mind-blowing thought.
It's a cosmic reality check, for sure. That's the future event horizon, the point beyond which we can never, ever receive information.
So they're saying dark energy could be tied to the past, the present, or even the future. It's like it's outside of time itself.
It's a wild idea, and that's what makes it so exciting. But how do you actually test something like that? You can't exactly build a holographic universe in a lab, can you?
That would be pretty cool, though, wouldn't it?
Yeah.
But yeah, I don't think our current technology is quite there yet.
Maybe someday. But these researchers, they found a clever way to test these ideas. Instead of trying to create dark energy in a lab, they decided to see how it would behave in different scenarios, how it would affect the universe around it. And to do that, they focused on something called perturbations.
Perturbations? Is that a scientific way of saying they poked the universe with a very long stick?
You could say that. Basically, perturbations are these tiny fluctuations in the density of matter and energy in the universe.
So like ripples in space-time.
Exactly. And those ripples, they're what eventually lead to the formation of, well, everything. Galaxies, stars, planets, you name it.
Okay, so they're pretty important, but how do you even begin to study perturbations in something like dark energy, especially if it's, holographic? It's like trying to create a ripple in a hologram itself.
That's the million-dollar question. And that was the biggest challenge for these researchers. Because THDE doesn't treat dark energy as a typical fluid or a field, those usual ways of analyzing perturbations, they just wouldn't cut it.
So what did they do? How do you go about studying ripples in, well, the fabric of reality itself?
They got creative. Instead of looking at perturbations in the dark energy itself, they focused on the future event horizon. Remember, that boundary is closely tied to THDE in this model.
Right. Okay.
So by calculating how this horizon was perturbed, they could essentially get a glimpse into how the dark energy itself was behaving.
That's brilliant. Instead of looking at the ripples in the water, they looked at how the shoreline itself was changing.
Exactly. Now, to keep things manageable, they decided to focus on scalar perturbations. Those are essentially the simplest kind of fluctuations you can have.
The most fundamental ripples in the cosmic pond.
Precisely.
Okay, so they simplified things a bit to get to the core dynamics. Makes sense. So what happened? Did they manage to break the universe with all this poking and prodding?
Thankfully, no. What they found was far more interesting than a broken universe, I'd say. They started running simulations where they played around with two main parameters in the THDE model.
Oh, a cosmic control panel. I like where this is going. Tell me more. So they're messing around with the cosmic control panel, tweaking these parameters.
Right.
What did they find? Did the universe explode? Did it turn into a giant bowl of petunias? What happened?
Well, thankfully, no explosions or petunias.
That's always a plus.
The universe is much more resilient than you might think.
Okay, that's good to know.
What they found was that for some values of those parameters, those perturbations, those ripples they were looking at,
Right.
they actually, some of them smoothed out over time. Kind of like, calm down.
So even with this exotic dark energy, things could still be stable.
Exactly. It's like the universe has this built-in balancing mechanism.
Fascinating. But you said for some values...
Right. So for others, the perturbations actually grew.
Grew. But I thought we were talking about dark energy. Shouldn't everything be flying apart?
You would think so, right? But here's where it gets really interesting. They found that as they increased that gamma parameter, the one connected to Tsallis's entropy.
Right, the weirdness factor.
Exactly. The higher they set gamma, the slower those perturbations grew.
Wait, so more exotic entropy, more weirdness led to less structure forming. That's counterintuitive.
It is. And that's why this research is so exciting. It suggests that dark energy might play a much more complex role in the evolution of the universe than we thought.
It's like it can either push things apart or help them clump together, depending on the cosmic settings.
That's a great way to put it. And remember how we talked about how they initially simplified things by ignoring matter perturbations?
Yeah, they didn't want to make the universe angry by poking it too much all at once.
Right. Well, when they added those matter perturbations back in, it had a huge impact.
Really?
The way those horizon perturbations behaved, it changed significantly. It's like they were only looking at one piece of the puzzle before.
So even though dark energy might be this dominant force, it's still part of a bigger interconnected system.
Exactly. It's not acting in isolation. And they even found that if they introduced a direct interaction between dark energy and matter, it could actually make those perturbations freeze even faster.
So more stability, but at the cost of independence. It's like dark energy is being tamed by the rest of the cosmos.
It's a delicate dance.
Mm-hmm.
And remember those three contenders for the infrared cutoff, the stage size of our holographic universe?
Yeah, the Hubble horizon, the particle horizon, and the future event horizon.
Well, they found that when they used the inverse Hubble parameter, that measure of the universe's expansion rate, the whole fate of the universe, how those perturbations evolved, it all changed drastically based on the value of gamma.
So just by tweaking these parameters, we can explore all these different possible universes. Some stable, some chaotic, some where galaxies form like crazy, others where they're few and far between.
It's like opening a door to a multiverse of possibilities.
This has been an incredible deep dive.
It has.
We started with dark energy and somehow ended up talking about holograms and the very nature of reality itself. What a wild ride.
That's what I love about cosmology. There's always something new to discover.
It's the ultimate frontier.
Yeah.
Well, on that note, we're going to have to wrap things up. But thank you so much for joining us on this journey into the mind-blowing world of Tsallis holographic dark energy. Until next time, keep looking up and never stop questioning the nature of the universe.